Okay, so let's address some properties of angles. Before we do that, let's explain what an angle is. An angle is a degree of rotation between a reference line or ray to another. Okay, lines are infinite. For the most part, we're going to just look at line segments, right? A line segment, a line is basically, it extends both ways, right? A line segment is just one aspect of that line, and a ray is just a line that goes in one direction, right? So this is a ray, this is a line, this is a line segment. Okay, and line segments have endpoints, right? So there's not too much to understand here. Basically, you can express an angle. Let's say I'm using two rays here, but you can express an angle as a degree of rotation between two rays. So here's an example of that. So I have a blue ray here and I have a red ray here, and if I wanted to rotate the blue ray to get to the red ray's position, I'm rotating it this way. And this degree of rotation, this amount of rotation, is the angle. Now we represent angles using different variables, right? So most common ones is the theta sign, alpha, beta, but you might see other letters, and these are just Greek letters, so they seem intimidating, but they're really not. They're just letters from the Greek alphabet. And basically, higher the angle, the more the rotation that occurs, right? We're gonna look at different types of angles. Where two of these rays or lines meet, this point is called a vertex. Okay, just food for thought, right? And this is basically a reference line or ray. Okay, so it depends on what you guys call it or what you guys use, right? For the most part, we're going to be looking at line segments in these subsequent examples. Let's look at the different types of angles first. So when an angle, let's say we're using theta to represent the degree of rotation, if the angle is greater than 0 but less than 90 degrees, this is what we call an acute angle. Okay, so an acute angle is basically less than 90 degrees. Alright, here's an example of an acute angle. If I had two line segments, right, and I was looking at theta here, right, theta here would be an acute angle. The other type of angle, this one's a really special one, if theta is equal to 90 degrees, this is what we consider a right angle. So a right angle is usually indicated with this little square, right? And these two lines would be perpendicular, or these two rays would be perpendicular. So this is a right angle. Now if theta is greater than 90 degrees, but less than 180 degrees, this is what we call an obtuse angle. Okay, so here's an example of an obtuse angle. Okay, you kind of want to construct these angles using a ruler. So here's an obtuse angle, right? When theta is equal to 180 degrees, I'm just going to highlight this. Okay, so these are just some of our conditions. Theta is equal to 180 degrees. This creates a right angle. Okay, so here's an example. Sorry, a straight angle, not a right angle. Sorry, guys. This is a straight angle. Okay, so this is a straight angle. It's 180 degrees. Right. Now, if theta is greater than 180 degrees, okay, but less than 360 degrees, this one isn't as common, but we get an angle. It's called a reflex angle. And you can notice that the circle here is on the outside, right? So a reflex angle is just it's larger than a straight angle. And we know that a full rotation counts for 360 degrees. For the most part, we're measuring angles. Angles can be measured in degrees or radians, but what we're going to be looking at is degrees, right? There are other forms of measuring angles, but these are the more common ones that you guys will see in your secondary school careers. For the most part, radians are actually more exact than degrees, but for the time being, we'll just look at it in degrees, right? So those are some examples of angles that you might see, right? Next, what we're going to do is we're going to look at some of these properties, right? So let's start with 90-degree angles. Okay, so here's a right angle, and let's say we had another line here. Okay, and I've split this into two angles. Okay, so this is a 90-degree angle, and I split this into two angles. I'm going to just label this guy alpha, and I'm going to label this guy beta. Okay, and you can understand that in this statement is true where alpha plus beta is equal to 90 degrees. Okay, if two angles add up to 90 degrees, then alpha and beta, these two angles, are complementary angles. So complementary angles are angles that add up to 90 degrees. Okay, so these are angles that add to 90 degrees. Okay, and let's say we had a straight line. Okay, we had a straight line like this. Okay, and we know that straight lines constitute a straight angle. Let's say we had another divider like that, and these two angles, let's call this guy alpha, let's call this guy beta. Well, we know that a straight angle, or straight line, will have a 180-degree angle. As a result, we can understand that this statement, alpha plus beta, is equal to 180 degrees. Okay? And in this case, alpha and beta are examples of what we call supplementary angles. Okay, any angles that add up to 180 degrees are supplementary angles. Okay, so keep that in mind. Where so you can say that alpha and beta are supplementary to each other. This is a really common concept that we're going to explore when we're actually looking at questions, right? Now, the next thing we're going to look at here, if we have a polygon, so let's try a polygon here. If we had a polygon, like a triangle or a square, okay, we'll say we have a rectangle here. Okay, a polygon is any two-dimensional closed figure. Okay, so we have this polygon here and there, right? And as a result of polygon, let's say that we'll name these polygons. Let's call this guy vertex A, B, and C, and let's call this guy D, E, F, and G. We'll call this G, right? So basically, all of these angles on the inside of these polygons actually add up to a specific value. Okay. Now we know three-sided figures are all triangles. Four-sided figures are called quadrilaterals. Quadrilaterals. Right, so here's a triangle, and we know that the sum of the angles of a triangle add up to 180. All quadrilaterals add up to, let me just write that again. All quadrilaterals add up to 360. And the way we know this, there is actually a formula here. The total number of angles, the sum of the total number of angles is equal to 2n minus 4 times 90. Okay, so this is a really useful equation. You could also simplify this. If you wanted to factor this, you could factor out 2 here. You get n minus 2 times 90. So another way you can represent this this equation is 180 n minus 2. So you can use either or. Okay, but these are this equation will tell you what the sum of the total interior angles, or the angles on the interior, add up to for any polygon, right? So this is the sum of interior angles in a polygon. Okay, so the interior angles are the angles on the inside. Angles located on the inside of a polygon, right? And they add up to a certain amount, right? So if we use this formula and say we had a pentagon, that looks like that, right? It has 5 sides, right? If we wanted to use this formula to calculate the sum of those angles, all we have to do, n is basically the number of sides in the polygon. So what we do here is we basically plug this in. I'm just going to use the 180 times n minus 2 equation. So you get 5 minus 2. Okay, sorry guys, I'm just going to make some space here. Okay, and you basically will get 180 times 3, which is 540. Okay, so the sum of all the angles in a pentagon, for instance, will give you 540 degrees. Right, so these equations are really useful, and that's another property of angles that we need to look at: interior angles. All right, now let's take a look at some other properties of angles, and there's also angles on the outside. Okay, so what I'm going to do here is for each vertex, I'm going to draw a line that's going to be supplementary to the line segments. Okay, so it's going to be a line here, and this is specifically for the angles in question, right? So you have an angle here and an angle here, right? So I'm just going to draw a line here. Okay, now these angles, right, we'll call this theta 1, right, theta sub 2, theta sub 3, right? These are what we call exterior angles. Okay, so theta sub 1, theta sub 2, and theta sub 3 are exterior angles, and the sum of all exterior angles, in a polygon add up to 360 degrees. Okay, so this is something that's also useful. It may not be as common, but it's good to understand. And this is really an extension of basically supplementary angles, right? You can see that angle B and theta 2 are supplementary, right? And you can make this statement that angle B plus theta 2 should be equal to 180. You can do the same thing for all of these, right? But that's the idea. This is something that you should kind of understand, and they should all add up to 360. So keep that in mind, right? So those are some properties of angles with figures and lines, right? Polygons and lines. What we're going to do next is we're going to be looking at another case of properties of angles, but this time we're going to be looking at the case of with parallel lines. Okay, so this is going to be a little different. Alright, so let's take a look at some properties of angles, this time with parallel lines. So let's first introduce what are parallel lines. Well, parallel lines are lines that don't meet. So let's say that we have two lines here. This is line 1, this is line 2. Line 1 is parallel to line 2. And this symbol means parallel to. And you guys can think about this as a set of railway tracks rails that don't meet, right? They're lines that never meet, so those keep extending forever. Okay, so that's what parallel lines are. And there are a few properties that we're going to be investigating with these parallel lines associated with angles. Now the first set of properties are what we call co-interior angles. So what are co-interior angles? Well, if you have two lines, right, like that, and then this line is parallel to this line, right? In this case, these two angles, we'll call this angle alpha, angle beta, these two angles will add up to 180 degrees. Okay? So you can almost think of them as being supplementary, but these angles are co-interior angles. So alpha and beta are co-interior angles. This only occurs when you have this characteristic C-shaped pattern. Okay, so try to memorize these patterns, guys. It'll really help you when you guys are looking at this, so just tend to memorize like that. Those are examples of co-interior angles. You have these two sets of parallel lines. You can imagine that this is really useful in trapezoids. So the next example that we're going to be looking at let's say we had two sets of parallel lines like that. And we had a line that basically went across this. Let me just fix this a little bit, right? And you had two angles, alpha and beta here. Well, if this line is parallel, and you can only do this with parallel lines, if this line and this line was parallel, then alpha is equal to beta. And you can say that alpha and beta are examples of what we call alternate angles, or alternating angles. Okay, so alternating angles have this characteristic Z shape, right? Alternating angles. Okay, so there's a characteristic Z shape, so you can memorize that as well. Okay, so let's highlight that as well. Okay, and another example are angles called corresponding angles. Okay, and corresponding angles, so let's say that we had these two lines like that. Okay, well, three lines like that, and then let's say that these three are parallel. So this is parallel to this, and this is parallel to that, right? And let's get some angles here. Say this is alpha, beta, gamma, let's do delta. All right, these are just some examples of angles. And in this case, this angle is actually going to be equal to this angle, and this angle is going to be equal to this angle. Okay, and the way we memorize this is there's this characteristic F shape. So I'm just going to show you guys that. So basically, if you look at this, there's a characteristic F shape here, right? And the two angles on the outside, well, one on the inside of the first parallel line and one on the inside of the second parallel line are equal, right? So I would just kind of memorize this shape. So alpha is equal to gamma, and in this case, you can pretend the beta and the delta are this inverted F. So it kind of looks like that, if you guys see it. Okay, so it's this upside down F, and beta is equal to delta, right? And these are examples of corresponding angles. Sorry guys. Corresponding angles. Okay, so alpha and gamma are corresponding, and beta and delta are corresponding. Okay, so for corresponding angles, I would just memorize this F shape. Okay, so these are just like some of the principles. I think the best way to illustrate this is to do questions. So you want to kind of understand some of these properties with parallel lines, as well as some of the properties with just regular lines, arrays, as well as figures that we've looked at. Okay, let's solve for the missing angles, right? So we're going to use some of these angle properties that we discussed with lines, polygons, as well as parallel lines. Let's take a look at some of these missing variables. We have alpha, beta, gamma, we have x here, right? Let's solve for these. Let's start with alpha. So starting with alpha, we know that alpha plus 72 degrees is equal to 180 degrees. And the reason we know this is because of the fact that we have a set of parallel lines from AB and CD, right? Because AB is parallel, line segment AB is parallel to line segment CD. As a result, we can create this co-interior pattern. Okay, so these are examples of co-interior angles, right? So then we can say that alpha is equal to 180 degrees minus 72 degrees, which if you calculate this is 108 degrees. Okay, so alpha is 108 degrees, and the reason for that is because of the fact that alpha is co-interior to angle C. Okay, so it's co-interior to angle C, and they add up to 180. So that's one of our solutions. Okay, And your reasoning is really important, guys, because it shows, it basically shows that you didn't just figure out the angle with dumb luck. You will not be using a protractor in this because of the fact that this is all going to be based on algebra, right? So you want to explain your reasoning, right? So now we know alpha. So we know alpha, this is 108 degrees. This is an obtuse angle, right? Let's solve for beta. Well, if we're solving for beta here, beta is located there. If we're solving for beta, we can see that beta and angle C should equal 180 degrees. So as a result, beta, we're given angle C, it's 72 degrees, is equal to 180, right? Beta is equal to 180 degrees minus 72 degrees, which is also 108 degrees. And you can use the reasoning here that beta is supplementary to angle C. Okay, now another way you can look at this, and you'll get the right answer this way as well, you can also say that if you look at this closely, actually, if you look at this closely, you can see that CD is parallel to AB, and you create this F pattern, right? And you can see that alpha and beta are examples of corresponding angles, right? So you can also say alpha should be equal to beta, and as a result, therefore, beta should be equal to 108 degrees because of the fact that beta is corresponding to alpha. These are sets of corresponding angles. Is a corresponding angle to alpha. So either way you spin it, you should get the same answer, right? So there's multiple ways of perceiving it. All of these answers are correct, right? So it doesn't really matter which way you look at it, right? So beta is equal to 180 degrees, okay? So we understand that there, you get the same answer, okay? Let's take a look at E, and you can also notice that if you look at this figure upside down, you can notice here that side length EF is also parallel to side length CD, and side length EF is also parallel to side length AB. Okay, so that's important to understand. And we can also look at the set of corresponding angles, and as a result, we can see that, you know, angle C and angle gamma, right? Gamma is equal to angle C because of the fact that gamma and angle C are corresponding angles. Okay, so that's our reasoning behind that. Okay, so that's your reason. Okay, that's your reasoning behind that. And so as a result, we've uncovered yet another set of angles. So this is 72 degrees. Okay, so this is 72. And we determined that B was 108. Okay, so you can start to see that we are filling in the missing pieces. All right, let's go on to the other side. And because we've said that AB and CD and EF are parallel to each other, you know, you can reverse the arrow here. And you can also employ the same logic on this end. Okay, so what we can do here, right, so we have a series of corresponding angles. So angle F should be equal to angle D, so this should be 84 degrees. And as a result, for X, if you're looking at X, X should be X plus 84 degrees, or X plus angle D here is equal to 180 degrees. Okay, so having said that, we can notice here that X here is basically 180 degrees minus 84 degrees, and X here is equal to 96 degrees. Okay, so here this is going to give us 96 degrees, and the reason for this, you can say that X and angle D are co-interior angles. Right, so you can use the same idea here, and you can see that they're co-interior because of the fact that they create this C shape. Okay, so we basically solved all our variables, and that's really how you can use these angle properties to get some information on missing angles. Alright, let's take a look at some relationships between triangles, and the types of triangles that I'm going to be looking at are going to be the difference between congruent triangles and this notion of similar triangles. Okay, so let's take a look at defining congruent. Well, if two triangles are congruent, if two or more triangles are congruent, they basically have the same angles and they have the same side lengths. Okay, so this is what you want to remember from any two polygons or any two figures that are congruent, that they have the same angles, they have the same corresponding angles, right? Corresponding angles means that they have the same angles that are positioned equally, and they have the same side length. So let's take a look at this example here. We have, this is triangle ABC. Okay, you can see that the triangle is labeled as vertices, so this is triangle ABC. Here we have triangle DEF. Okay, and in this case, we want to look at, first of all, its side lengths and its angle. So if we look at angle B, it's corresponding with angle E, right? Because this is basically the only obtuse angle in the triangle. And we can imagine here that this triangle DEF, is positioned differently than triangle ABC. However, it could still be the same triangle, even if it's positioned differently, right? So we just have to transform this. We just have to rotate it or reflect it to get back to this, right? So you can see that the angles match, right? And if you look at side length AB here, right, and I'll look at this definition similar afterwards, but if we look at side length AB here, it's equal to side length FE. And if we're looking at the magnitude here, the magnitude of side length AB, the length of side length AB is equal to the length of side length FE. Okay, so we can see that here. We can also see that side length BC is equal to its corresponding side length DE. Okay, although the diagram here isn't drawn to scale, we're mainly just looking at the values that are given, right? So then we can compare the longest side, which looks like side length AC on triangle ABC, and this is actually equal to the longest side on triangle DEF, and this is actually side length DF. Okay, so these two side lengths are going to be the same. So all of these side lengths are the same. Now let's take a look at the corresponding angles, right? And one way you can show corresponding angles, you can draw these rings around the angles. So let's say we're looking at the 43 degrees. I'm going to draw two rings for this, right? And you can see that it mimics angle F, right? So you can see that angle B is equal to angle E, angle A is equal to angle F, right? And you can also see that if I do three rings here, right, angle C is equal to angle D. So because all three side lengths and all three angles are equal between the two triangles, they are congruent triangles, right? So therefore you can say, therefore triangle ABC is equal to triangle DEF. And that shows that the two triangles are congruent, that they're equal to each other. The two triangles are congruent, they're exactly equal to each other. So that's a key point. Let's take a look at this notion of triangles that are similar, because if we take a look at the set 2 of triangles, here we can see that the side lengths aren't the same, right? So it's not going to be an identical triangle. Congruent means identical. Let's take a look at this notion of a similar triangle. Okay, so two triangles are similar if they have the same angle, so they contain the same angle, contain the same corresponding angles, and they also contain proportional side lengths. So what is a proportional? What does it mean when we say proportional side lengths? Well, a proportional side length is basically side lengths that differ by scale factor. Okay? So basically if you multiply a certain value to all the sides in one triangle, you can get to the other triangle. Now I'm going to show you guys this by looking at these two triangles. Right, let's label these accordingly. Right, let's consider this guy A, B, and C, and let's call this guy D, E, and F. Okay, so let's take a look at these sets of new triangles, ABC and DEF, right? I could have changed up the letters, it doesn't matter, right? So this is triangle ABC, this is triangle DEF, right? And we want to show that these two triangles are similar. So what I'm going to do here is I'm going to compare the corresponding sides, and you get the corresponding sides with their angles. Now remember that all similar triangles, when you're comparing similar triangles, they have to have the same corresponding angles. So you can see that we're missing an angle in each of these triangles, right? We know that the sum of all the interior angles of a triangle add up to 180. So if we wanted to find this missing angle, we would do 115 plus 27, we subtract it from 80, and we should get 42 degrees. Okay? And if I did the same thing for a triangle DEF, if I add these two together and I subtract by 180, we should get 27 degrees. Okay? So, sorry, 43 degrees. That should be 43. So there should be there's a little typo here. This should actually say 43 instead of 42. This is 43 degrees. Okay? So in both cases, you can see that the angles are the same, right? And in that sense, we know that they can potentially be similar triangles, because similar triangles have to have the same corresponding angles, right? So the 43 degrees here, right, this angle corresponds with this, right? This angle corresponds with this, and this angle corresponds with this. Okay, so the angles are the same, right? So angle A is equal to angle D, angle B is equal to angle E, and angle C is equal to angle F. Okay, so we understand that. Now what we want to do is let's compare the side lengths, right? So angle AB is being corresponded to DE, right? However, they're not the same. Now, in order to find a scale factor, we're going to divide AB over DE. Okay, so the magnitude of AB over the magnitude of DE, right? And this is going to give us 3 centimeters over 2 centimeters, and this is going to be 1.5. So what this is saying is that side length AB is 1.5 times that of side length DE. Okay, so it's a ratio basically. And do the same thing with the other set of corresponding sides, BC, and divide this by side length EF. And you're going to get 4.5 centimeters divided by 3 centimeters, and that's going to give you 1.5. So this is saying that BC is 1.5 times as big as EF, right? And we're going to do the same thing with the last set, right? AC over side length EF. You're going to get 6 centimeters over 4 centimeters, which is also 1.5. So you can notice that all of these sides are proportional by 1.5 times, from triangle DEF to ABC. So you can actually even say that triangle 1.5 times triangle DEF is equal to triangle ABC. Okay, so this 1.5 is, if it's consistent, this 1.5 here represents something called a scale factor. A scale factor exists when you can multiply a certain factor to all the sides and you'll get another similar triangle. All similar triangles contain a scale factor, and that's what the proportional side lengths are. They contain a scale factor, right? And you can multiply it by the scale factor to get the similar triangle, right? So put another way, if we wanted to kind of represent this, right, we can say that a scale factor exists when you have a ratio between the corresponding sides, right? So I'm just going to erase this portion here. But if this is true, if you have a ratio of corresponding sides, and if I write it out, if I write it out this way, right? If I see that side length AB over side length DE is equal to side length BC, this side length over this side length EF, which is equal to side length AC over side length DF, then that means that these two triangles are similar. Okay, so this is the idea, and we're going to look at some questions to kind of emphasize this topic. So if triangles don't fit in the realm of being congruent or similar, then we just say that they're neither. Okay, so let's take a look at some examples of this. Okay, let's identify if the triangles are similar, then state the corresponding angles. So we have two triangles here. We have triangle CDE and we have triangle EFG, right? You can see that they are somewhat rotated. Okay, so I'm just going to redraw them right here. So this is our triangle. This is C, D, and E, right? And this is 4 centimeters. This is 2.5 centimeters. This is 4.5 centimeters. And this one's inverted, so I'm just going to write it like that. I'll draw it like this. Okay, and this is E, F, and G. So this continues from our point E. Okay, so this is 9 centimeters, this is 5 centimeters, and this is 8 centimeters. Okay, now we aren't actually given any angles that are measured, and we can assume that these two lines here are parallel. Okay, so assuming that the angles are the same, right? Assuming that the angles are the same, let's figure out if these are in fact similar, right? So if the triangles are similar, then the angles should be the same, right? So if we want to determine if the triangles are similar, then what we're going to do here is we're going to compare the sides, right? I'm going to compare FG to CD, right? Because the reason I'm comparing the side length of FG to CD is because if you invert this triangle, if you flip it upside down, it should kind of look like that, and then it's easier to kind of envision, right? So then this would be C, D, and E, right? And this would be 4 centimeters, right? You can always redraw it, guys. This is 4.5 and this is 2.5. So you're going to kind of use your imagination a little bit. Okay, so you can compare this, if I reflect this triangle, it doesn't change the side length, and compare it to EFG. Anyways, let's compare FG, the side length of FG, over the side length of CD, right? So that's going to give us 8 centimeters or 4 centimeters, which is basically 2. Okay, let's compare then EG to ED. Okay, EG to ED. Let me just see if I redrew that properly. E, C, and D. CE, okay. Okay, let's compare. So it seems like the triangles are reflected. So let's compare EC actually EG to EC. Okay, so if we compare EG to EC, we can see that EG is 5 centimeters and EC is 2.5 centimeters, and this fits the proportionality of 2. So we're starting to see that there is this common scale factor. And then we're going to do the last side. I'm going to compare, let's do EF to ED. Okay, so EF here is 9 centimeters, ED is 4.5 centimeters, and this is 2. Okay, so we can see that there is a common scale factor, right? So there is this common scale factor that can be seen here, right? And well, you can see this a lot easier if you just kind of flip this triangle. So if I do flip it, right? If I do flip it, then this would be D, this would be C, and this would be E, right? And EC is basically 2.5 centimeters, right? So if I flip it, right, if I do this mirror image, then this is 4.5 centimeters and this is 4 centimeters. So you can actually see this a lot easier if you flip it. We can see that there is a scale factor, and the reason I flipped it is because now that we know that there is a scale factor, because of the fact that these 3 side lengths between the 2 triangles are equal, the ratios are equal, right? FG, side length FG over CD is equal to side length EG over EC, which is equal to side length EF over ED. Okay, let's not do a complete absolute value because we're looking at, this just means magnitude, guys. And this is all equal to 2, so 2 here is your scale factor. And what you want to do to find the similar angles here if you draw it like this in yellow, you can see that this angle should be similar to this angle should be the same as this angle, and this angle should be the same as this angle. Okay? Because all similar triangles have the same corresponding angles. So those are your corresponding angles, and that's what they wanted you to show. But we can also show that these are similar triangles, and the way we can write that two triangles are similar, we can say that triangle CDE is similar to triangle FGE, or DCE if you want. No, sorry, FGE. Yeah, so I wrote it out the first time. FGE, right? So this means similar to, right? So you can use this symbol to show that the two triangles are similar to, but that's literally the idea, all right? So this is pretty useful. We'll show you this when we apply this to word problems. Okay, let's say if we wanted to determine if the triangles that we're comparing are congruent, similar, or neither, right? So here we have two triangles. We can see triangle M. You know what? Let me just change colors here. We can see two triangles. We can see triangle MNO, and we can also see triangle MPQ, which is the larger triangle here. Okay, so I'm going to compare MNO and MPQ. Because those are the only triangles that we can really actively see. And in this case, we can also see there should be a 90-degree angle here, guys. Sorry about that. Okay, so here we can see that M and O is already inscribed here, but MPQ is a combination of M and O and NPQO, which is a quadrilateral, right? It's a trapezoid. So let's redraw out. Let's redraw out MPQ, triangle MPQ. So if I'm redrawing out triangle MPQ, let's do it here. Okay, so I'm just gonna, so this is your MPQ, I'm just creating a sketch here, so just to help us out. And you can see that MP is the combination of MN and NP, which is basically 9 centimeters. Okay, PQ should be 7.5 centimeters, and MQ should be a combination of MO plus OQ, right? So if I add 7.8 with 3.9, I'm going to get basically 11.7. Okay, so just going to double check that. But yeah, it's 11.7, right? So these are our lengths of the side lengths, right? So now what we want to do is let's compare M and O with MPQ. Let's see if these are actually similar triangles. Okay, and if they are similar triangles, they should have the same corresponding angles. So let's do a comparison here. Let's compare side length PQ. Let's compare side length PQ with side length NO. Okay, so PQ here is 7.5 centimeters, NO is 5 centimeters. So if I crunch this out, 7.5 divided by 5, I get 1.5. Okay, so there's 1.5 times. Now let's compare another set of side lengths. Let's compare MQ, so side length MQ over the magnitude of side length, I think they're both called MQ by accident. MO, sorry, there you go, by MO, right? Kind of got a little tripped out with MQ and MO, but let's compare MQ with MO. Okay, I'm just going to highlight this so we can actually see this better. But this is the triangle that we are comparing it to. Oops. Okay, guys, try to use a ruler for this stuff. But I'm just kind of showing it to you guys. Okay, so these are the two triangles we're comparing it to. And MQ is basically 11.7. MO is 7.8 centimeters. Right, cancels out. And if I divide 11.7 divided by 7.8, I get 1.5 as well. Okay, and then I'm going to do the last set. And remember that all three sides have to be proportional by the same scale factor, MP over MN. And you basically get 9 centimeters over 6 centimeters. If you crunch this out, this is also 1.5. So you can imagine here that PQ, silent PQ over NO, is equal to silent MQ over MO which is equal to side length MP over MN is equal to 1.5, and we have this scale factor, and as a result we can say that therefore triangle MNO should be similar to triangle MPQ. So these triangles are similar, and as a result we can create corresponding angles. We know that we can kind of attribute this right angle from there, right? So as a result we can say that this angle should be a corresponding angle to this, right? These two right angles are the same, and then these two side length O should be equal to side length Q, right? So side length M should be consistent, right? Side length side length N is equal to angle N is equal to angle P, and angle O here is equal to angle Q, right? You can also use, you can also call this angle NOM if it helps, is equal to angle PQM. It's the same thing, okay? So when you have similar triangles, you have the same corresponding angles, and as a result, these two triangles are similar, okay? So that's your correct answer. They're not congruent because they have different side lengths, and as a result, by default, if they're similar, they're not neither. Okay, so that's... Alright, let's calculate the length of the missing side. So here we have a triangle. This triangle actually has a smaller triangle, as shown, and these two lines here are parallel, right? So we want to find side length x, right? Because we have right angle triangles, this also tells us at first thought that we can use the primary trig ratios. We can use SOHCAHTOA. Okay, so SOHCAHTOA just tells us sine is the opposite side of the hypotenuse, cosine is the adjacent side over hypotenuse, and tan is the opposite side over the adjacent side. So we can use the primary trig ratios as long as we have right angles. Okay, we can't use it when we don't have right angles. Okay, so now that we have that done, what you want to consider here is if we want to find, because we're trying to find side length x, which is on the secondary triangle on the inside of this bigger triangle, we need to find some angle within that triangle. Okay, just to make our discussion easier, I'm going to call this A, point B, C. I'm just labeling this arbitrarily, E and F. So I want to find an angle somewhere in between A, B, and C. Okay. Now we also understand that if side length EF is parallel to side length BC, then as a result, this angle here, and we'll call this guy angle theta, right? Theta plus 75 degrees should be equal to 180 degrees. And we know this because theta and 75 degrees are co-interior angles. Okay, so recall from previous math courses that co-interior angles create the C pattern as long as they are parallel, right? Angle A plus B should be equal to 180 degrees. So it creates a C pattern. They're basically going to be parallel. Okay? So that's what co-interior angle is. So in this case, we isolate first. Theta is equal to 105 degrees. Okay, so this is actually 105 degrees, right? And because this is also a straight line, this angle here, angle C, plus 105 degrees should be equal to 180 degrees because of the fact that they are supplementary angles. Okay, so you need to kind of understand how your angles work in figures, right? So go back and review some of these concepts of complementary, supplementary, co-interior, interior angles, alternate angles, corresponding angles, all of these things just to kind of help you with this material, okay? So in this case, we know that angle C here should be equal to 75 degrees, right? So you could have done it that way. You can also see that because BC is parallel to EF, you can say that this 75 degrees is equal to this 75 degrees because there are corresponding angles, right? So angle C can be equal to angle F because of the fact that they are corresponding angles, and corresponding angles make this F-shaped pattern, right? So just recall this F-shaped pattern. If these two lines are parallel, this is A and this is A, and this is B, and if you have another line that's parallel, then this would be B as well. Okay, so these are corresponding angles. So we know this is 75 degrees, and now that we know this angle, and we have the side length here, we're going to try to find what the value of x is, right? Now, however, we're not really given anything else besides that, right? Now, on second look, if we do look at this, we don't actually need to find this angle, right? So I'm just kind of overviewing that these type of angles are useful. In some cases, you're going to be using them to solve for, with trig, you're going to be using them to solve for missing side lengths. In this case, however, it's actually easier if we just look at the triangle as a whole. If we look at this triangle here, because we know that this is 75 degrees, and we also know that this whole length here is x plus 2.5. Okay. We also know the base is 2 centimeters, and this whole thing is a right angle, so we'll just use this whole thing to find it, right? Now, if I look at the opposite side of angle F, right? The opposite side of angle F is basically side length AE. Okay. Now the hypotenuse is basically side length AF. Okay, so the hypotenuse is AF. Okay, so this is your hypotenuse. I'm just gonna keep it consistent. So the hypotenuse is AF, and you also have side length EF, which is your adjacent side. Okay, so the piece of information that you're trying to solve for here is x, right? And we are given our adjacent side, so the best trig ratio that we can actually use here is the cosine ratio. So I'm going to do cosine 75 degrees. If you do cosine 75 degrees, I'm going to do cosine is adjacent over hypotenuse, right? So the adjacent side here is 2 centimeters, and the hypotenuse here is x plus 2.5 centimeters. Okay, so let's try to solve for this. So we have cosine 75 degrees is equal to 2 over x plus 2.5, right? And what you could do here is you could actually solve for cosine 75 first, right? So let's change it into a decimal. So when we take out our calculator, make sure your calculator is in degrees here, right? Cosine 75. So this is about 0.259. I'm just going to use 3 decimal places, is equal to 2 over x plus 2.5. What you want to do here is you want to solve for x. So what I'm going to do is I'm going to do the reciprocal. If I flip this, I can also flip that, or you can cross multiply, whatever you want to do, right? And in this case you get, I'm just going to rewrite it here, but x plus 2.5 over 2 is equal to 1 over 0.259, right? And because this is over 2, what I'm going to do now is I'm going to multiply this side by 2 and multiply this side by 2 as well, just to cancel out the 2, and you get x plus 2.5 is equal to 2 over 0.259, and if I want to solve for x is equal to 2 over 0.259 minus 2.5. So x here is equal to, and I'm just going to punch this in my calculator, 2 divided by 0.259 minus 2.5, and you get 5.22. Okay, so x is equal to 5.22. So that's how you can actually solve for this, right? So so just try to kind of scan the question, try to find the easiest method of doing this, right? At first glance, I thought we would just kind of look at the smaller triangle, but I was missing information, so I went back to the bigger triangle. But it is important to kind of understand some of how these angles work. So I would say go back and review that, because there will be questions that will involve trig that also uses some of these angle properties. Okay, so we'll take a look at some more of this stuff. So we know that trigonometry is the study of triangles. And when we're looking at these primary trigonometric ratios, we're going to be specifically looking at right angle triangles, right? So these guys are only used for right angle triangles. And these ratios can help us to look at the relationship between an angle, a reference angle, and its particular side lengths in a triangle, right? Now, we can understand that angles, when you use theta to represent angles in a triangle, or basically angles in any kind of geometric shape, theta is going to be representing angles, and we know that this total sum of angles in a triangle should be 180 degrees. Okay, so keep this in mind, right? And the primary trigonometric ratios that we're going to be looking at include the sine, cosine, and tangent ratios. Okay, so these are some of the values of the ratio. These are like formulas that you want to kind of memorize. Sine of an angle is basically equal to the opposite side over the adjacent side. Sorry, opposite side over the hypotenuse. Cosine of an angle is equal to the adjacent side over the hypotenuse, and tan of an angle is equal to the opposite side over the adjacent side. And notably, you can memorize these using the mnemonic SOHCAHTOA. Okay, so using this mnemonic, you can see that S here represents sine, C represents cosine, and T here represents tangent. Okay, so sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tan is opposite over adjacent. Now let's take a look at what do these side lengths mean, right? So if we have a triangle here, say this is our triangle, right? It has to be a right angle triangle. You can only use these primary trig ratios for right angle triangles. And let's say that we label this triangle A, B, and C. Okay. You can note here that this right angle here represents that it is a right angle triangle. The side length opposite of the right angle is always the hypotenuse. Okay, so I'm going to explain what the hypotenuse is, but the hypotenuse, I'm just going to use HYP to abbreviate that, but the hypotenuse is the longest side in a right angle triangle. Okay, so it's the longest side in a right angle triangle, and basically we can also label, instead of writing this as hypotenuse, we can also label this based on the angles of our triangle, right? So we can understand that I've labeled this triangle ABC. Each of these capital letters represent a vertex, and basically they also represent the angle. So this is angle A, this is angle B, this is angle C, and this is angle B, right? Opposite of each angle is a respective side length. So this is side length A, this is side length C, and this is side length B. And we represent side lengths using lowercase letters. We use angles and vertices or vertices in capital letters. Okay. Now, so we said the hypotenuse is always going to be right across the right angle, but let's say we want to look at the opposite or the adjacent side. Well, to look at the opposite or the adjacent side, we need a reference angle, right? So we can use angle A or we can use angle C. We tend to use acute angles for reference angles, right? So we can't really use this right angle. So having said this, let's say that instead of labeling these angle A and angle C, I label this a different way, right? Let's call this guy angle alpha, and let's call this guy, let's call this guy angle beta. Okay, so this is beta, this is alpha, right? And we can understand that if I'm taking a look at, we can understand that angle alpha and angle beta should be equal to 90 degrees. Okay, that these are two complementary angles, right? Complementary angles are angles that add up to 90 degrees, because we know that the total sum of angles in this triangle should equal 180, and this is already 90, right? So these are complementary angles. Complementary, well, they should be spelled with an E. Complementary angles. And let's take a look at the ratio, right? So we can find that if we use angle alpha as a reference angle, then this side length A is our opposite side. Okay, so this is my reference angle. A is my opposite side. This side length B here will always be a hypotenuse, so as a result, this is my adjacent side. Okay, let's take a look at angle beta. So if I'm looking at angle beta, you can notice that, if I'm looking at angle beta, you can notice that now this side becomes the opposite side. This hypotenuse will still stay the same, and then as a result, this becomes the adjacent side. So depending on our reference angle, it changes the ratio. So let's take a look at our primary trig ratios for alpha. Say we looked at sine alpha. Sine alpha is basically equal to the opposite side, A, over the adjacent side, over the hypotenuse, I did that twice, over the hypotenuse, B, right? So this is going to be equal to A over B, it's opposite over hypotenuse. Now if we take a look at cosine alpha, right, then we're going to have the adjacent side, C, over the hypotenuse, B. And if we take a look at tan alpha, we'll have the opposite side over the adjacent side, so it's going to be A over C. Okay? Now let's take a look at if beta was a reference angle. Okay, so let's say that sine beta here is now, the opposite side is now going to be C. It's going to be C over hypotenuse, which is B. Cosine of beta is equal to the adjacent side, right? So if we look at beta, the adjacent side now becomes A. We're going to get A over the hypotenuse, B. And tan beta is going to give us opposite, which is now C, over the adjacent side, which is basically A. Sorry, over A, right? So now we get C over A. And you can actually notice a few things here. You can notice here that sine alpha is basically equal to the ratio of cos beta. And we can also notice that sine beta is equal to the ratio of cosine alpha. Okay, so there should be some kind of link here, right? And we want to kind of explore this, right? So if we do explore this, we can understand that we know alpha plus beta is 90 degrees. We can understand that beta can thereby be written as 100 is 90 degrees minus 90 degrees minus alpha. Okay, so having said that, this becomes true that sine 90 degrees minus alpha is equal to cosine alpha. Okay, and it's true the other way around as well, right? That alpha is 90 degrees minus beta, right? So in that sense, we can understand that cosine 90 degrees minus beta is equal to sine beta. Okay, and this is going to be true for whatever angle you look at, right? So this actually brings up a really important identity that we're going to be exploring later, which is basically called the cofunction identity, right? You can write one trig ratio in terms of another, right? So this is really useful to take a look at this triangle, and basically you can understand here that sine theta is basically cosine 90 degrees minus theta, right? So this is your cofunction identity, and we're going to take a look at this later on. But basically you can convert one angle into its equivalent cosine angle, right? You can convert the sine ratio into its equivalent cosine ratio, and you can look at the value of the angle that will keep the ratios constant. Okay, so we'll kind of explore this further on. So previously we took a look at our primary trig ratios, which include the sine ratio, sine theta, which is equal to the opposite side over the hypotenuse. We also looked at the cosine ratio, which was equal to the adjacent side over the hypotenuse, and we also looked at the tan ratio, which was equal to the opposite side over the adjacent side. And we noted that these primary trig ratios were only used for right angle triangles. As long as there was a right angle triangle, we could use these ratios, right? Now these guys also have an associated reciprocal ratio. Now reciprocal basically means that we're dividing anything by 1, and when we take a fraction, if we have like a over b, right, the reciprocal, which is 1 over a over b, if we do the reciprocal of this, we'll actually get b over a, right? And any fraction multiplied by its reciprocal will give us 1, right? That's really the purpose of a reciprocal, right? It just basically a fraction, a reciprocal fraction times its original fraction will give us 1, right? Because you can see here that's AB over AB, right? Anyways, so these guys actually have reciprocal ratios, and the reciprocal ratio of sine theta, 1 over sine theta, is equal to something called cosecant theta. Okay, so cosecant is the reciprocal of the sine ratio. The reciprocal of cosine is something called secant, right? Right, and secant is 1 over cosine theta. Yes, it's called secant. And the reciprocal of tan is something called cotangent. Cotangent is 1 over tan theta, right? So having said this, using this definition, right, cosecant theta is basically the hypotenuse over the opposite side. Secant theta is the hypotenuse over the adjacent side, and cotangent is the adjacent side over the opposite side. Okay, so let's keep this in mind for further discussion. Alright, for the following triangle, determine the indicated values, right? So we know this is a right angle triangle, so we can use our primary trig ratios. If we want to solve for x here, what we can do here is we have a reference angle is 42 degrees. We have the hypotenuse, which is 5 centimeters, and this is where the primary trig ratios become really useful, is that we can understand that if you wanted to solve for x, using the reference angle 42 degrees, this is going to be our opposite side, this is going to be our hypotenuse, and this will always be our hypotenuse, this won't change, right? Because we can basically, because there's a right angle present, right? So the side length that's always across the right angle is always along the side. And we can solve for x by using the sine ratio because we have the opposite side and we have the hypotenuse. So you have 3 bits of information. If you know 2 out of the 3, you can solve for the missing link, right? So I'm going to do sine 42 degrees is equal to the opposite side x over the hypotenuse, which is 5. In this case, x is equal to 5 times sine 42 degrees. And in this case, x is equal to 5 times sine 42 if we punch this out. And you can notice that you can actually find the value of the ratio if you plug it into your calculator. So make sure the settings of your calculator is in degrees, right? And we'll take a look at other measurements of angles later on, right? So as long as your angle is in degrees, you can kind of solve for this, right? So in this case, sine 42 is equal to 0.6691. Okay, so I'm just going to use 4 decimal places for the time being. So 0.6691. If I multiply this by 5, I basically get 3.3457. And if I round this off, let's round it to 2 decimal places, it's 3.35 centimeters. Okay, so we actually solved for x, right? So it's 3.35 centimeters, right? Before solving for y, we can actually note that beta here, 42 degrees plus beta, should equal 90 degrees because these two are examples of complementary angles, right? So you could have actually started by doing that first. So beta here is 90 degrees minus 42 degrees, which is basically, should be 48 degrees, right? So this is 48 degrees, okay? And put the degree sign and note that it is in degrees. It's important to keep the units on. And then what you can do here is you can solve for y really 3 different ways, right? You can use reference angle beta, you can use reference angle 42 degrees, or you can use Pythagorean Theorem. And we can actually note that you'll get the same value. So I'm going to just show you guys that, but remember that right angle triangles allow us to use Pythagorean Theorem. So we can understand that x squared plus y squared is equal to 5 squared, right? Because a squared plus b squared should be equal to c squared according to Pythagorean Theorem. And in this case, we already solved for x. So 3.35 squared plus y squared, which we were trying to solve here, is equal to 5 squared. So y squared is equal to 5 squared minus 3.35 squared. And if I calculate this, right, I get 25 minus 3.35 squared. So that's going to give us 13.778. Okay, and y here, if I square root it, right, because you want to solve for y, not y squared, you get square root of 13.778. And in this case, what you're going to get here, 3.71 approximately. Okay, so I'm just going to keep all answers in two decimal places. So this is 3.71 centimeters, right? I'm going to show you that you're going to get the same answer by evaluating it using the trig ratios. Let's tell me to use beta just to kind of show you that you can do this multiple different ways, right? And so one of the beauties of math is that you don't have to do it a set way. You can approach problems in multiple different ways. Now, if I use beta here, and we know beta is 48 degrees, I'm going to be using, because this becomes my reference angle, y becomes the opposite side, right? So I'm just going to use sine 48 degrees, right, which is beta, is equal to the opposite side, y, over the hypotenuse 5. Y is equal to 5 times sine 48 degrees, and y here is equal to 5 times sine 48, which is also 3.7157 centimeters. So it's approximately 3.72 centimeters, which is basically what we have here, right? So it's like 3.715. I could have had a rounding error here that's like caused a slight deviation, but you can notice here that it's the same value, right? So this just indicates that there's multiple different ways you can do this. We can also use the 42 degrees to solve for y by using cosine. Let's see that. I'm going to show you that it gives you the same value. Like if I do cosine 42 degrees, then it's adjacent side. So this becomes the adjacent side, right? Is adjacent side y over the hypotenuse 5, then y becomes, if I multiply 5 to both sides, you can solve for y. So 5 times cosine 42 degrees, and y is equal to 5 times cosine 42, which is approximately 3.7157 as well, right? So ideally, we would probably want to round this to 3.72 centimeters, but at the end of the day, it's the same thing, right? So this can show you guys that you can do, you can approach trig questions when you're solving for a missing side multiple different ways, and if the case does present itself, you can also employ Pythagorean Theorem. So all of these things are related. So that's what the power of trig really. All right, let's solve for the missing unknowns. So v and u using some trig ratios, right? So this is a right angle triangle, so we can use our primary trig ratios, and we can use SOHCAHTOA, this mnemonic, right? Sine is opposite over hypotenuse, right? So sine theta is opposite over hypotenuse. Cosine theta, is equal to adjacent over hypotenuse, and tan theta is the opposite side over the adjacent side. So this is what you want to kind of keep in mind, right? And let's start by solving for an angle. And we could use Pythagorean Theorem, however, I am not going to employ that because the question is specifically using trig ratios, but I can show you guys afterwards that the Pythagorean Theorem and trig ratios, they basically are cut from the same cloth, and they are going to give you about the same answer, right? So there is a sense of consistency there, so it's a good thing to kind of look at afterwards. Let's start by finding angle u first. So if I'm trying to find angle u, I'm going to do here. So this is angle u here, and I'm going to draw an arrow across it, and this side length v here is the opposite side. The side length across the 90-degree angle is the hypotenuse always, and the hypotenuse is the longest side of a right angle triangle, and the remaining side here is the adjacent side. Okay, so what I want to do here is, if I wanted to look at the ratio that gives me the most amount of information, I can see that my adjacent side and hypotenuse is given, so I'm going to use the cosine ratio. So I'm going to do cosine theta, well in this case cosine u, because we're using angle u as a reference, is equal to adjacent side 5.18 centimeters over the opposite side, which is 20 centimeters. Centimeters cancels out, and we get cosine u is equal to 5.18 over 20. And if you want to solve for u, you have to get rid of the cosine. So we do something called a cosine inverse. Okay, and when you take the cosine inverse of cosine, the cosine and cosine inverse cancel out. Now whatever you do to one side of the equation, you have to employ to the other side. Keep it consistent. So u is equal to the cosine inverse of 5.18 over 20. I'm going to plug this in my calculator. Make sure you guys put brackets around this, right? But usually you can find it on your calculator if you press shift on the cosine sign, or the symbol, right? And you get 5.18 divided by 20, and you get about 74.989 degrees. I'm going to round it to my nearest degree. I'm going to round it to 75 degrees. So u is 75 degrees. Okay, so this is 75 degrees, right? We have this 90-degree angle here, so we can actually find the remaining angle, right? That this angle and u should add up to 90 degrees because they're complementary, because the sum of interior angles adds up to 180, right? So this plus 90 should equal to 180. So this has to be 15 degrees. Now let's find side length v. Okay, so now we are given the angles, we're given the side lengths. Let's use the trig ratios to find side length v. Well, we're given u now. What I want to do now is I want to find v. So I'm going to find a ratio that has the opposite side on the numerator to solve for it, and I can either use the sine or tan ratios. So what I'm going to do is I'm going to use a tan ratio this time. So tan, and I'm going to use u. Tan u is equal to the opposite side over the adjacent side, and the opposite side here is v. The adjacent side is 5.18, and tan u is basically, we calculated for u, is tan 75 is equal to v over 5.18. What I'm going to do is I'm going to solve for v. So I'm going to multiply by 5.18 to cancel this out. Whatever I do to one side of the equation, I'm going to do the same thing to the other side. So v here is equal to 5.18 times, and make sure when you're using tan or cosine or sine, you're putting a bracket around it, right? V is equal to 19.332. Well, I just rounded to 19.3 centimeters. Okay, so v is equal to approximately 19.3 centimeters. So now we've used our trig ratios and we've effectively solved for our unknown variables. Okay, let's apply some of this trig knowledge that we've learned, and let's apply this to some real-world problems. Right? So here we have a problem-solving question. Justin leans a 2.5 meter ladder at a 57-degree angle to the floor to go up to the attic. How high is the entrance to the attic? Okay, so these word problems are really key, and the best way to do these word problems, I would really advise you guys to kind of draw out some diagrams. Okay, so we basically have some kind of house here, right? Because we have an attic on top of the house, right? So the attic is at some kind of elevation. So let's say that this is the attic here, okay? Right, this is like the attic window or something, right? So just don't mind the really crummy drawing. What you're gonna do here is what Justin's doing anyways, is he's leaning a ladder on the floor to get to the attic. Okay, so this is your ladder. You know, let's say that this is the ground here, right? So yeah, don't mind the poor drawing, guys. So this is your ladder, right? So just kind of make it a condensing ladder. Okay, so this is your ladder. Okay, and basically the ladder here is 2.5 meters. Okay, and this is on the ground, and we can assume here that this is basically a height, right? So this is a height, so it's always 90 degrees to the base, and this angle that it makes with the floor or the ground, whatever you want to call it, right? This angle that it makes here is 57 degrees. Okay, so if you want to find how high is the entrance to the attic, you're basically finding the height, right? And you can only use these trig ratios as assuming that this is a right angle triangle, so that's why it has to be a true height. And as a result, I can use one of my trig ratios. So what you're given here, if I look at the side length opposite of this angle, this is the opposite side, right? The side length that is opposite the 90 degrees is the hypotenuse, and as a result, this should be the adjacent side. Okay, and if you want to solve for h here, I would try to use a trig ratio that employs the opposite side on the numerator. So you can either use the sine ratio or the tangent ratio. I would tend to use sine because of the fact that we're actually given the hypotenuse, right? So sine theta is the opposite side over the hypotenuse. You're not given the opposite, but you're trying to solve for it, but you're given the hypotenuse, right? So in this case, sine 57 degrees is equal to h over 2.5. If you want to solve for the height, I'm going to multiply by 2.5 to this side to cancel it out. Whatever I do to that side, I'm going to repeat that to the other side. So h is equal to 2.5 times sine 57 degrees, and h here is equal to, and I'm just going to punch this in my calculator. Make sure that when you are multiplying this, you put brackets around the sine 57, so you get 2.096, approximately 2.1 meters. Okay, so how high is the entrance to the attic? It's approximately 2.1 meters. Okay, so that's how you can apply trigonometry to word problems. Alright, let's solve for the following triangle by finding all missing sides and angles. Now, in this case, we're not given any angles. We know this is a right angle triangle, so we can utilize our primary trig ratios, but we are given two sides, right? Now, you can actually solve for side length x by using Pythagorean Theorem, right? So I'm going to just do that out really quickly, but I also want to demonstrate that you can do this by using trig. Now, if we do use Pythagorean Theorem, we can understand that c squared, which is the hypotenuse, and the hypotenuse is always located across from this angle, from the right angle. C squared, the hypotenuse, minus b squared, which is any of the other two sides, is equal to a squared, right? So in this case, a squared is x, right? So we can understand that 7.2 squared minus 4.1 squared is equal to x squared. So therefore, x is equal to the square root of 7.2 squared minus 4.1 squared. Okay, so in this case, we can see that if I crunch this out in my calculator, it's 7.2 squared minus 4.1 squared, and this is going to give us 5.9186 centimeters. Okay, I'm going to keep it into 4 decimal places because I want to see how accurate my trigonometric procedure in calculating this missing side will be to this Pythagorean theorem. Okay, so we calculated that x is 5.9186 centimeters. Now, the big question here is how do we find these angles, right? Now, to find the angles, I'm going to use, for alpha, let's use rad here. Okay, so this is angle alpha. To find alpha here, right, we can notice that this becomes the opposite side. So x is the opposite side, right? Let's say we label this side length A. Let's call this guy C, and let's call this guy B, right? So this is side length C, this is side length B, and this is side length A, right? And it's just another way of looking at it. And so this is your opposite side here, and this will always, C will always be a hypotenuse, so this is going to become the adjacent side. B is our adjacent side, right? And we can understand here that if we didn't solve for x, we do have the value of our adjacent side over hypotenuse. So cosine of alpha is equal to 4.1 over 7.2. Okay, let's assume that I didn't solve for x here. Okay, I'm going to just look at the information that I've given, and if you figure out what this value of this ratio is, 4.1 divided by 7.2 is going to give us 0.5694. Okay, so we get 0.5694. Now, in order to solve for alpha, I need to get rid of this cosine, and we do something called an inverse. It's called the cosine inverse. We do the cosine inverse of cosine alpha, and this actually cancels out the cosine. So each function has its own inverse, right? So if you have sine theta, right? If you do the sine inverse of sine theta, then you basically get theta. If you do cosine inverse of cosine theta, you basically get theta because the cosine and the cosine inverse cancel out. And if you do the tan inverse of tan theta, you basically also get theta. So the inverses just cancel out the ratio, like the value of the ratio. And in this case, we can see here that cosine inverse of cosine alpha, it will give us alpha, But whatever you do to one side of the equation, in order to keep it the same, you have to do it to the other side. So cosine inverse of 0.5694. So now you can see that alpha is equal to the cosine inverse of 0.5694. And if I punch this in my calculator, you should see that alpha is equal to 55.29 degrees. I'm going to round to the nearest degree, so let's do 55 degrees. So if alpha is 55 degrees, you can then solve for beta, because we can understand that beta is complementary to alpha, right? Alpha and beta are complementary angles. And in this case, beta should be equal to 90 degrees minus alpha, which is 55 degrees, which should also be 90 minus 55 is 35 degrees. Now let's say that we want to solve it a different way. Well, using beta here as my reference angle, then this becomes the opposite side, right? This will become the adjacent side, and then the hypotenuse will still remain at 7.2. So in that sense, we can understand the sine of beta using our previous values will give us 4.1 over 7.2, right? And we found the ratio of this, so sine of beta is equal to 0.5694, right? We calculated the ratio of this. So beta here, if you want to solve for beta, what you need to do here is you need to do the sine inverse of both sides. So sine inverse of sine beta is equal to the sine inverse of 0.5694, and then the sine inverse and the sine cancel out, so we get beta is equal to the sine inverse of 0.5694. So if I do that in my calculator, you actually get a different value. You actually get the same value. You get like 34.708 degrees. If I round that to the nearest degree, it's about 35 degrees. So you can actually see that you get the same value. Okay, this is really useful, and it does really help us to kind of understand this, right? So you can actually see that beta will give us the same value. Now, in that sense, right, so we know how to solve for alpha and beta, right? So alpha here is 55 degrees, so rounding into the nearest angle, and beta here is, let's say, beta here is 35 degrees if I round to the nearest angle. And I want to solve for x. Well, you can use any of these two angles now, right? Let's just use alpha, and you'll see that you'll get the same answer. So let's say we're using alpha. So alpha, this will become the opposite side, so we can understand the sine of alpha, which is basically 55 degrees, is equal to basically x, the opposite side, over the hypotenuse, 7.2. If I want to solve for x, I'm going to multiply 7.2 to both sides, cancels out. X is equal to 7.2 times sine 55 degrees, and in this case x is going to be equal to, so 7.2 times sine 55 degrees is going to be equal to about 5.8978, right? You can notice that it's very close. Like this is going to be 5.9, this is going to be 5.9, right? And one of the reasons because is I rounded the angle off, right? So if you do keep it as accurate as possible, right? I had 55.29, right? So if I did 7.2 times sine 55.29, you can see that you'll get 5.9187. So it's very close. It's exactly the same, right? Like if I do sine 55.29 in my calculator, you can actually note that you would get 5.9187. Right, so if you actually use the original value, you can see that the margin of error between Pythagorean Theorem and utilizing trig here, right, the trig value and using Pythagorean Theorem, using the trig ratios in Pythagorean Theorem, these are very close, right? So now we've solved for x, and we can say that x is equal to, let's say, 5.92, right? And that's basically our triangle in a nutshell. We've solved for a triangle. So you can use a combination of these trig ratios, the inverse of the ratios, Pythagorean theorem to basically solve out a right angle triangle. So it's really useful to understand. Alright, so let's take a look at special angles. So special angles are angles that we will actually know the exact value of their ratios for a respective function, like a sine, cosine, tan, or its reciprocal functions, right? And these angles include 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Okay? Now for the first set of angles, the 30 degrees, 45 degrees, and 60 degrees, we can determine the exact value of their respective ratios for each of the three primary trig functions, right? We can find the exact value of these ratios by using something called a special triangle. Okay, so we're going to be using a special triangle for these three values to demonstrate that. And then for these other values left over, the 0 degrees, the 90 degrees, the 180, the 270, and the 360, we're going to be using something called a unit circle. So I'm going to start with the demonstration of these special triangles, and then we'll take a look at the unit circle, right? Okay, so I'm going to start the special triangle depiction of these special angles. We're going to find the values, exact values of their ratios for 30, 45, and 60 for the sine, cosine, and tan functions. Okay, so let's start with our first special triangle. I'm going to call this special triangle number 1. It's not its particular name, but I like to kind of differentiate between the two. And you guys have to just memorize this. I haven't had to construct it, but this is technically an isosceles triangle. Okay, so let's say that this is your isosceles triangle here, and then this is, and these have to be right angle triangles because these are primary trig ratios. Okay, this is side length of 1, side length of 1, and then this is square root 2. Okay, so I'm just going to clean that up a little bit. Sorry about that, guys. Okay, so this is your right angle triangle. These are the side lengths of 1, right? You can notice that these are the same. And the angles associated are 45 degrees and 45 degrees. We know that an isosceles triangle will have two it's the same size, and as a result, two same angles, right? And we can notice that we can actually find the exact value of one of these angles, because the other angle is the same thing. It has to be an acute angle. You notice that sine 45 degrees is basically equal to, and this becomes a reference angle, so let's just do it here. So this is my opposite side. The hypotenuse is always across from the right angle, so this is the hypotenuse, and this is the adjacent side. So you can actually see here that sine 45 is 1 over square root 2, right? Now this ratio has a radical in the denominator, and we prefer not to have a radical, so I'm just going to multiply by square root 2 to both the numerator and denominator, so you actually get square root 2 over 2. So sine 45 is equal to square root 2 over 2. I'm going to be using this ratio value more consistently because of the fact that it's in better form. And if we take a look at cosine 45 degrees, well, we'll actually see that it's the adjacent side over the hypotenuse, and you'll actually get the same ratio, 1 over square root 2, which is square root 2 over 2, right? And this actually kind of coincides with what we showed earlier, that sine theta is equal to cosine 90 degrees minus theta, right? So you can notice here that sine 45 degrees is equal to cosine 90 minus 45, which is equal to cosine 45. So they actually have the same ratio. So that's one way we can actually see that, right? So you actually get square root 2 over 2. And tan 45 degrees is basically equal to opposite over adjacent, which is 1. So therefore, the values for the special triangle number 1 here, right, we can notice that sine 45 degrees is square root 2 over 2. Cosine 45 degrees is square root 2 over 2. And tan 45 degrees is 1. Okay, so those are the summary of our values for 45 degrees. I'm just going to make a box here. So make sure you guys memorize this, but really the idea is just memorize the special triangle here, right? So if you memorize the special triangle, you can actually come up with these values, right? Now the next special triangle that I'm going to be looking at here is basically going to help us to find 30 degrees and 60 degrees, right? So I'm just going to clear some room here, so I'm just going to erase this out. Okay, so now we're going to look at the other ratios, the exact value of the ratio for the other angles, 30 degrees and 60 degrees, by using these sine, cosine, and tan functions. Okay, so this time our triangle is going to look something like this. Whoops. Okay, so the triangle is going to look like this. And it's going to have a side length of 1, 2, and square root 3. Okay, this angle here is 60 degrees, and this angle here is 30 degrees. Now, a quick way of kind of remembering how to create this special triangle is what we could do here is we take an equilateral triangle. Okay, let's say that this is our equilateral triangle. We take our equilateral triangle, right? I didn't draw the scale, but kind of just bear with me here. Let's say that this is 2 units by 2 units by 2 units, and then this is 60 degrees by 60 degrees by 60 degrees. What we do is we basically take our magical scissors here and we cut this guy in half. Okay, so we cut this guy in half, right? And when we cut this guy in half, we actually create a right bisector. Okay, so when you create a right bisector, what happens here is you create a 90-degree angle, and when you cut this in half, look what happens, right? So you basically end up with this. You can see that the 2 unit is retained. This guy becomes 1 unit, and half of the 60 degrees is going to give you 30 degrees, and you also create this 90-degree angle. So this is a right angle triangle, and that's how you get this triangle. So that's a good way to memorize it if you guys, need some kind of backstory to help you with that. And then we can figure out some of our ratios. So let's start with our reference angle of 30 degrees. Okay, so I'm going to start with 30 degrees here. Okay, and in this case, now this becomes the opposite side, right? Across from the right angle will always be your hypotenuse, and then this guy, as a result, will become the adjacent side. Okay, so now we can see here that sine 30 degrees is equal to opposite over hypotenuse 1/2. Cosine 30 degrees is equal to adjacent over hypotenuse, which is square root 3 over 2. And tan 30 degrees is equal to opposite over adjacent, which is basically 1 over square root 3, or you can write this, if you multiply by square root 3, as square root 3 over 3. This is more preferable, right? So we have our values of 30 degrees for each of these trig functions. Now let's take a look at the 60-degree version, right? So if we take a look at the 60-degree version, I'm going to just get rid of this, just get rid of the coloration here. Whoops, got rid of our entire triangle by doing that. Okay, so let's say this is our triangle, right? And basically we can note here that the hypotenuse would be conserved, right? Still 2 here. And this time we'd be looking at 60 degrees. Okay, so let's take a look at this angle now. Okay, so if I'm looking at this angle, right, this is the opposite side. So I'm just going to erase this. So now this guy becomes the opposite side. The hypotenuse is still conserved, and this is your adjacent side, right? So now you can see here that sine 60 degrees is equal to opposite over hypotenuse, square root 3 over 2. Cosine 60 degrees is basically adjacent over hypotenuse, which is 1/2, and tan 60 degrees is equal to square root 3 over 1. You can also see that this cofunction identity is still conserved, right? Now we can see that sine theta is equal to cosine 90 minus theta, and cosine theta is equal to sine 90 minus theta. And you can notice this by just kind of comparing these two, right? Like if I compare sine 30 with cosine 60, they'll have the exact same value, right? But also if I compare this cosine 30, if I compare cosine 30 with sine 60, you'll see that it has the same value as well, right? So this will kind of work for all scenarios, right? And these are our values of our special triangle. To summarize the exact values of our ratios regarding the functions of our primary trig functions of our special angles, right, we looked at two special triangles here, right, and this was special triangle 1, and then this was special triangle 2, right, and this kind of helped us to determine the special angles 30 degrees, 45 degrees, and 60 degrees. If I make a summary chart regarding this, okay, so I'm just going to construct this, okay, where we have theta on top here. This is 30 degrees, 45 degrees, and 60 degrees, right? Let's say that we have, this is sine theta, right, our sine function, cosine theta, cosine function, and tan theta, right? We showed that sine 30 here was the value of a half, sine 45 was square root 2 over 2, and sine 60 is square root 3 over 2. Okay, cosine 30 here is square root 3 over 2, and it's equal to sine 60, right? Using, remember that we looked at the cofunction identity. Cosine 45 was the same as sine 45. Once again, you can determine that using the cofunction identity, square root 2 over 2. Cosine 60 is 1/2, which is the same as sine 30, right? And then tan 30 here was square root 3 over 3. Tan 45 was 1. And tan 60 was square root 3 over 1. So these are some of the values that you want to look at. And you have to kind of memorize these values because they're going to become really important as we kind of progress through this. Right? Let's say I gave you a question where we had evaluate, and this is where you wouldn't be using a calculator. Evaluate for each expression. And let's say we had sine 45 degrees times cosine 30 degrees minus, let's do tan 30 degrees. Okay, so let's say we had something like this. In this case, sine 45 was square root, let's use a different color, square root 2 over 2. Cosine 30 here is basically square root 3 over 2, and tan 30 is basically square root 3 over 3. In this case, if we multiply these two, right, so we get 2 times 2, which is 4, square root 2 times square root 3 is square root 6, minus square root 3 over 3. And then what we want to do is, in order to combine the numerators, I'm going to find a lowest common denominator, make the denominators the same. So I'm going to use 12 here. So in that case, I'm going to multiply this guy by 3, and this guy by 4. So you get 3 square root 6 minus 4 square root 3 over 12. And that's really as far as you can go. You can't really simplify this any further. So this is basically your answer. Okay, so that's really the idea. You have to be able to fully simplify, you have to be able to fully memorize all these values, and it's going to become really useful later on as we look at just evaluating expressions, but specifically it's going to be really useful in our discussion of related angles, where we're going to be looking at a related acute angle to find values of obtuse angles. So guys, really just memorize these values. It's going to be really important. We'll also be looking at the other special angles, which include 0 degrees, 90 degrees, 180, 270, 360. I'm going to show you guys how to calculate for that, but we're going to be introducing the unit circle. Okay, so earlier we said that our special angles were angles where the trig functions would give us ratios that we would know the exact values of, right? So in the special angles we discussed were 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, 180 degrees, 270, and 360 degrees. Okay, so out of all of these, out of this entire set, we just looked at these three, 30, 45, and 60, and we identified them using the special triangles. Now, what I'm going to do now is I'm going to look at the rest of the special angles, and I'm going to show you a way to find their values. And this method is going to be through the use of a unit circle, right? So I'm going to construct, in order to look at the unit circle, we need to look at angles in standard form, right? So I would advise you guys to kind of review that video regarding angles in standard form. Alright, so here's our Cartesian plane. I'm going to take a look at angles in standard form. So recall that if we're looking at angles in standard form, an angle is a degree of rotation from lines or rays, and one of the rays is a reference ray that we're going to be looking at, and it's called the initial arm. It's located on the positive x-axis, right? And the other ray here is basically going to be some angle at or away from the initial arm, and this is called terminal arm. And we also stated that the vertex was 0 and 0, and then positive rotations were counterclockwise rotations, right? Now, a unit circle is a special type of it's a special type or case of angles in standard position. We know that a full rotation here, if I did a full rotation, right? You know what? I'll use a different color so we don't have to. We know that a full rotation is going to give us 360 degrees, right? And full rotation is going to create a circle. Okay, so just don't mind my circle drawing abilities here, right? But assume that this is a circle, guys. Okay, so this is a circle. So full rotation of the initial arm, the terminal arm would give us a circle, right? We also stated earlier that we can look at the position of the terminal arm from the origin, from the vertex, which is 0 and 0, as a point x and y. Okay, so you can look at this position as x and y. Now, a unit circle is a special case where the terminal arm's length, which becomes radius if you have a full rotation, the radius of this circle here is going to be 1 unit. Okay? So the radius is going to become 1 unit, right? And a degree of rotation here, call this guy theta. The degree of rotation here is basically going to create a right angle triangle, right? Because this point can be expressed as x and y, this corner here, this dimension here is x, and this dimension here, this dimension here is y, and this dimension here is x. So therefore, the ratios of the angles are as follows. Sine theta here is going to call this guy r, right? Sine theta here is opposite over hypotenuse, so it's y over r, right? Cos theta is basically x over r, and tan theta is basically y over x, okay? Now there's a few things you want to kind of note here. We said that this unit circle has a radius of 1 unit, so r here is 1. So because r here is 1, then we basically sine theta is equal to y. Because r here is 1, cos theta is equal to x. And just from this, you can note that tan theta is y over x. Because sine theta is y, it's basically sine theta, and cos theta is x. We get tan theta is equal to sine theta over cosine theta. This is actually a really important identity that you're going to be using a lot later on. And this is, this is the quotient identity. Okay, so this guy here is a quotient identity, right? And basically tan of any angle theta is equal to sine of that angle divided by cos of that angle. Okay, so keep that in mind. So we understand that notion, but we also stated that points can be expressed as x and y, right? So using that notion, because sine theta is y and cosine theta is x, therefore points can also be expressed as cos theta and sine theta. So we can look at a position of the terminal arm by looking at the degree of rotation of its angle. Okay? Now, a few things to note here. Because we have a unit circle and the radius is 1, right? Then this point here, should be 1 and 0, because the radius from the origin, from the center of the circle to the outside of the circumference is 1 and 0. This point here should thereby be 0 and 1 if this is a perfect circle. This point here should be negative 1 and 0, and then this point here should be 0 and negative 1. So these are the 4 points that are associated with the circle, right? Now we can imagine that if the terminal arm was located at the initial arm as such, right, the angle here would be theta, it would be 0, right? So theta here would be 0 degrees. And the point of the terminal arm would be in the form of cosine 0 and sine 0. Now this is also equivalent to the coordinate in terms of x and y as 1 and 0. You guys see that? So as a result, we can understand that cosine 0 is equivalent to 1 and sine 0 is equivalent to 0. So these are the values associated with cosine 0 and sine 0. Let's try another one. Right, so this is when theta is equal to 0 degrees. Let's see what happens when theta is equal to 90 degrees. So if theta was equal to 90 degrees, now the terminal arm would be located here. Remember that rotations are relative to the initial arm. If theta is 90 degrees, if it's positive 90 degrees, this is a counterclockwise rotation 90 degrees, right? So we'd expect the terminal arm to be positioned there, right? And if we look at that, then this would be relative to the angle cosine 90 degrees and sine 90 degrees. And this would also be related to its point in this x and y coordinate 0 and 1. So this tells us that therefore cosine 90 is equal to 0 and sine 90 is equivalent to 1. Okay, so those are the values for cosine 90 and sine 90. Okay, let's take a look at another example here. Okay, so let's say that theta is equal to 180 degrees. So if theta is equal to 180 degrees, our terminal arm this time would be rotated all the way here to counterclockwise rotation. It would end up there, right? And in this case, we would have the point would be cosine 180 sine 180, and it would be equivalent to -1 and 0. So therefore, right, let's use a different color so we don't get mixed up. Cosine 180 is equal to -1 and sine 180 is equal to 0. That makes sense? Right? So that's basically 1/2 of a quadrant. Let's take a look at the next special angle. So we figured out values of this, we figured out values of 90, 180, let's look at 270 and 360, right? Okay, so I'm just going to erase this guy, because we'll get back to that afterwards. But let's take a look at when theta is equal to 270 degrees. Okay, when theta is 270 degrees, our terminal arm can be located here. Okay, so if a terminal arm is located there, then the point equivalent here is cosine 270 degrees sine 270 degrees. And this is equivalent to the point 0 and -1. So therefore, cosine, you know what, let's use blue here. So therefore, cosine 270 degrees is equal to 0, and sine 270 degrees is equal to -1. Okay? And for the last case, when theta is equal to 360, you can actually notice that we just get back to, if we did do the rotation from the initial arm, we just get back to 0 degrees. So it's the exact same values as 0 degrees, right? So if theta was equal to 360, right, then you'd have point cosine 360 sine 360. This is equivalent to 1 and 0, and you can see that cosine 360 is 1 and sine 360 is 0, right? So therefore, cosine 360 is equal to 1, sine 360 is equal to 0, and this is the same as cosine 0 and sine 0, okay? Those are the values of our respective special angles, 0, 90, 180, 270, and 360. Alright, to summarize everything we've kind of discussed, we looked at some of the functions, the trig functions, the sine function, the cosine function, the tangent function. We also looked at their trigonometric functions, which include the cosecant function, the secant function, and the cotangent function. And we also we looked at those ratios, and we also discussed this notion of special angles, which included the 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, 180, 270, and 360 degrees. And we discussed how these special angles, the exact values of the ratios, could be determined by using the special triangles, the unit circle. I'm just going to summarize all of this out for you guys. Right, so let's start with, these are just values of theta here. Right, so this is theta. And let's start with sine theta, cosine theta, tan theta, and then we'll also look at the reciprocal values, right? I would just recommend memorizing sine, cosine, tan, but I'm just going to put all of this out there for you guys, just in case you wanted to memorize the rest. I don't think it's useful, but it's better to memorize sine, cosine, tan, your primary trig ratios, and then for your reciprocal, you just have to take the reciprocal of their ratio values. You just flip the numerator and denominator. But I'm just going to put all of this out there for you because it does bring up a very important point that we will later on discuss when we study these, the behavior of their trig functions, of these trig functions graphically, right? So we looked at sine, cosine, tan. We'll also look at cosecant theta, which is the reciprocal of sine, right? Cosecant theta is 1 over sine theta, right? Secant theta is 1 over cosine theta, and we'll also look at cotangent theta, which is 1 over tan theta. Okay, so keep this in mind, guys. So I'm going to write secant theta here and cotangent theta here. Okay, I'm going to start with cosine and sine really quickly first. So for the unit circle, we had sine theta, sine of 0 is basically 0, cosine of 0 is 1. We also looked at, I think I briefly discussed the quotient identity, that tan theta, and I showed you guys this through the proof of the unit circle, that tan theta is equal to sine theta over cosine theta. So having said this, although we had values from the special triangles, which included 30 degrees, 45 degrees, and 60 degrees, where we actually determined tan theta, for the unit circle, you can actually just divide sine over cosine to find tan. So when you do tan of 0, for instance, right, so tan 0, let's just do it here. So tan 0 here is equal to sine 0 divided by cosine 0. Okay, so tan 0 is sine 0 divided by cosine 0. In that case, sine 0 here is 0, cosine 0 is 1, so tan 0 is 0 degrees. And that's how you would basically solve for it. Sine 30 degrees, we said was 1/2. Cosine 30 was square root 3 over 2, right? And as a result, tan 30, you could divide these two, right? And you can prove that here if you wanted to. So tan 30 degrees should be equal to sine 30 divided by cosine 30, which is basically equal to 1/2 divided by square root 3 over 2. If I simplify that, 1/2 times 2 over square root 3, so you actually get 1 over square root 3, which we simplified as square root 3 over 3, right? And we know this is true because by drawing the special triangle, this was square root 3 over 3, okay? Sine 45 was square root 2 over 2. Sine 60 was square root 3 over 2, which is the same value as cosine 30, and we looked at that notion that sine theta is equal to cosine 90 degrees minus theta, right, and vice versa, that cosine theta is equal to sine 90 degrees minus theta as well. Okay, so this is another thing that we investigated. So cosine 45, same value as sine 45 square root 2 over 2. Cosine 60 is the same value as sine 30, which is 1/2. Sine 90 was 1, cosine 90 was 0, right? And tan 90 as a result is 1 divided by 0, which doesn't exist. Okay, so 1 divided by, and whenever you have 0 on the denominator, it doesn't exist. Tan 45 was 1, tan 60 was square root 3 over 1, right? Sine 180 from the unit circle we determined was 0. Cosine 180 we determined was -1, and then 0 divided by -1 is 0. Right, sine 270 was -1. Cosine 270 was 0. Tan 270 is sine 270 -1 divided by cosine 270, which is 0. Doesn't exist. Right? Sine 360 was 0. Cosine 360 is 1. And tan 360 is 0. Okay? So those are the values for our primary trig functions, right? These are your primary trig ratios. Let's take a look at the reciprocal values, right? Cosecant 0 degrees is basically the reciprocal of sine. Now this is basically, for sine theta, this was 0 over 1, right? So it was basically 0. So cosecant is 1 over 0, which is undefined, right? Because this is 0 over 1. If you do the reciprocal, it should be 1 over 0. So this is undefined, does not exist, right? Secant, however, it's the reciprocal of cosine, right? So pretend that this is 1 over 1, so secant, you just flip it, so you'll get the same value, it's 1. Okay, guys? Right? Cotangent doesn't exist, right? So cotangent theta is basically, if tan theta is sine over cosine theta, then cotangent is cosine theta over sine theta, and sine theta doesn't exist, right? Well, sine theta is 0, right? So it's 0, 1, it also doesn't exist. Okay, so keep that in mind. Cosecant 30 is basically the reciprocal of sine 30, so it should be 2 over 1, right? Secant 30 is 2 over square root 3, and you guys can simplify this, right? You can write this, if you multiply by square root 3, right, you get square root 3 over 3. Okay, so I'm sure you guys know how to do the radical simplification, right? So it's 2 square root 3 over 3. And then cotangent theta is the reciprocal of sine, so you get 3 over square root 3. And if you multiply this guy out, right, you get 3 square root 3 over 3, which is basically square root 3. Okay, so square root 3. Cosecant 45 here is the reciprocal of sine, so it's going to be 2 over square root 2, which is square root 2 over 1. Okay, and same idea with secant. And then cotangent here is still 1. Okay. For cosecant 60 degrees, that's going to be the reciprocal of sine. So it's going to be 2 over square root 3, which we stated was 2 square root 3 over 3. Okay. The reciprocal of cosine 60 is 2 over 1. And then this guy here is going to be 1 over square root 3, which is basically square root 3 over 3. Okay, guys? Okay, so then we also have cosecant 90, which is 1, it's reciprocal. Secant 90, on the other hand, we know that cosine 90 is 0, so it's 1 over 0, so it doesn't exist. Okay, and cotangent also doesn't exist, right? Because you can see that it's sine is cosine 90. Oh, sorry guys. Wait, so cotangent 90 is equal to cosine 90 over sine 90, right? And that's going to give us 0 over 1. So this actually does exist. So cotangent would actually be 0 here, right? So there the restriction is gone now, right? So keep that in mind, right? So in this case, cosine 90 is 0, cosine 90 is 1, so that's why it will exist. And then we can figure out the rest. So cosecant doesn't exist because it's 1 over 0. Secant here will be negative 1. And then cotangent would be, let's do it out here. So cotangent cotangent 90, cotangent 180, just erase this out. Cotangent 180 is equal to cosine 180 over sine 180, and once again this is undefined as well, right? So this doesn't exist either. Okay, cosecant 270 is still negative 1. Secant 270 doesn't exist because you get 1 over 0. Cotangent 270, let's write that out. 270 is basically equal to cosine 270 over sine 270, when this is going to give us 0. Okay? We're 360 here. This doesn't exist because you get 1 over 0. This is 0 over 1. You flip it. Secant, you get 1. Right? And then cotangent 360 is going to be the same as 0 degrees, as also doesn't exist. Good? And this is your full out chart, guys. Okay, so it did take us a while, but for the most part, I would I would recommend kind of knowing these out. Once you know these out and you know the quotient rule, you can actually figure out the rest. And you know that reciprocals, you just flip the numerator and denominator, right? So, but I decided to do the full chart for you guys so you guys can have a good summary of all of this. All right, so that's the idea of special angles. So I would really recommend you to memorize this set that I've highlighted in yellow. All right, let's evaluate the following expression and reduce all fractions where possible. So we're going to be using some of the special angles that we looked at, some of the values that we looked at. Sine 60 is going to have a value of square root 3 over 2. So guys, you want to try and memorize that table that I constructed earlier. Tan 30 here is square root 3 over 3 minus cosine 45 is square root 2 over 2, and times sine 30 is 1/2. Okay, so what I'm going to do here is I'm going to simplify this. Now you're dividing these two fractions together, so you get square root 3 over 2. And when you're dividing two fractions, you multiply by the reciprocal, 3 over square root 3. You notice that square root 3 divided by square root 3 cancels out, and you actually get 3 over 2. Okay, so instead of writing all of this out, you can write that as 3 over 2, right? If I multiply these two together, you should get square root 2 over 4. So in my next line, I'm going to write 3 over 2 minus square root 2 over 4. And now what you want to do here is you want to find the lowest common denominator. So the lowest common denominator here is 4. So what I'm going to do here is I'm going to multiply this by 2 and this by 2. So you get 6 over 4. And then you basically can get 6 over 4 minus square root 2 over 4. And you could just leave your answer like this, right? We're trying to make sure that we have proper form where we simplify our fractions as much as possible and that the denominator doesn't have a radical. So this is our final answer to that question. So this was pretty straightforward. You just gotta have to memorize some of the trig ratios, all right? All right, let's take a look at a much more challenging example. Here we want to evaluate the following expression, reduce all fractions where possible. We want to make sure that there's no radicals on the denominator. Okay, so this time I've thrown in some reciprocal ratios. Now we need to kind of note here that cosecant 60 degrees is basically 1 over sine 60, and sine 60 is basically square root 3 over 2, so 1 over this is basically 2 over square root 3. Now I'll simplify the radical afterwards, right? But if you did want to simplify the radical, you can multiply by square root 3, so you get 2 square root 3 over 3. Okay, so that's the cosecant 60. Cosine 45 degrees, we know the value is square root 2 over 2. And cotangent 30 degrees, this is a reciprocal, is equal to 1 over tan 30 degrees, which is basically 1 over square root 3 over 3, right? And 1 over square root 3 over 3 is 3 over square root 3. And we can simplify the radical by multiplying by square root 3. So we get 3 over square root 3 over 3. So 3 times square root 3 over 3. So that's that for the first rational on the left. Now let's take a look at the second rational expression on the right. We have secant 45 degrees, which is 1 over cosine 45 degrees, which is basically 1 over square root 2 over 2, which is 2 over square root 2. Okay, so this is secant 45 degrees, it's 2 over square root 2, right? And we can multiply this by square root 2 to simplify it, so we get 2 square root 2 over 2, okay? Then we can take a look at sine 60. We know the value of this is square root 3 over 2. And we have cosecant 30 degrees, which is 1 over sine 30 degrees, which is 1 over 1/2, which is basically 2 over 1. Okay, now what I'm going to do here is I'm going to take all of these simplified values that I looked at and I'm going to put it back into my expression. So cosecant 60 we calculated was 2 times square root 3 over 3. Cosine 45 was square root 2 over 2. Cotangent 30 was 3 square root 3 over 3, right? And we're going to add this with secant 45, which we calculated was 2 square root 2 over 2, sine 60, which was square root 3 over 2, and cosecant 30, which is basically 2 over 1, right? And then if I simplify this, I'm going to multiply this out, right? So you get 2 square root 3 times square root 2 here is 2 square root 6 over 6. Okay, I'm going to divide this by 3 square root 3 over 3 plus, right, square root 2 times square root 3, so 2 square root 6 over 4 over 2. Okay, let's simplify this. Let's do this using a different color here. If I simplify this, I'm going to take a look at these two. 2 square root 6 over 6 times, because I'm dividing these two, I'm multiplying the reciprocal, 3 over 3 square root 3, right? And you can notice here that you get 6. 2 times 3 is 6, divided by 6 is 1. So you basically get square root 6 over 3 square root 3. And what we could do here is multiply by square root 3 to simplify this. And we get square root 18 over 9. Okay, so we get square root 18 over 9. I'm going to keep it like that for the time being. We can simplify that afterwards. So that's basically all of this guy here. So this is square root 18 over 9. And then let's take a look at this notion here. So let's take a look at the fraction on the right. And in this case, we get, I use a different color here. I use green. In this notion, we get 2 square root 6 over 4. For dividing by 2, we're multiplying by a half. We basically cancel this out. We get square root 6 over 4. Okay. So now in my next line, this is what I'm left with. Square root 18 you can actually write using radical expressions as 9 times 2, which is square root 9 times square root 2, which is 3 square root 2. So you're going to have to memorize you have to kind of know your radical properties, right? So this is 3 square root 2, right, over 9 plus square root 6 over 4, okay? And now between these two, what you're going to do is find the lowest common denominator. Well, between these two, let's say the lowest common denominator is 36. And multiply this by 4, and this by 4, this by 9, and this by 9. So now what I'm left with is 12 over square root 2 plus 9 square root 6 over 36. Okay, and this is as far as I can go. I can't really simplify this any further. Other than the fact is that I can basically try to reduce it, right, by dividing this, and this by 4. If I divide this by 4, right, so divide this by 4, you get 3. Divide this by, oh wait, not 4, sorry. Let's divide it by 3. Okay, let's divide this by 3, you get 4. Divide this by 3, you get 3. And divide this by 3, you get 12. So beyond that, your final answer, as far as you can go with this, is 4 square root 2 plus 3 square root 6 over 12. Okay, so this is the simplified form, and that's your final answer to this expression, right? So you can notice that this was it was pretty complicated as a question, but you can see if you do this step by step and you simplify this repeatedly, you can kind of solve for this very difficult trigonometric expression. All right, so that's the idea, really. So an example of an extension of trigonometric ratios to real-world scenarios include the angle of elevation and angle of depression. So you're going to see this used a lot in questions, right? What an angle of elevation is, basically, let's say we have a person here and they're looking up at a giant tree, right? So they're looking up at that tree. So this is the tree. Okay, so let's say this is like the top of the tree, right? And let's say that the person is located on the ground level here. Okay, these are the roots of the tree, whatever, right? I'll just kind of, oh, sorry guys. Let's just say it's like that. Okay, so there's a person that's looking at the top of the tree, and let's say that this is their eye. Okay, so this eye, that they're looking at it horizontally, this is their horizontal eye level. We'll call this the horizontal axis. Okay, and when they're looking up to the top of the tree, right, this is something called the line of sight. Okay, and the angle that is made between the horizontal axis and the line of sight, this angle here, this is called the angle of elevation. I'm going to call it theta sub e. So this is the angle of elevation. Now the angle of elevation always creates a 90-degree angle on its opposite end. So this is going to be a true height. Right now, obviously, if you wanted to look at the height of the tree, you'd also have to factor in the height of the person, because their eye isn't located on their feet, it's located on their head, right? But this is just to give you an idea of what this will look like, right? So once again, these calculations are approximations, but if you wanted to make exact calculations, you'd have to put a bunch of other factors in your calculations, right? So this is an angle of elevation. It occurs when you're looking up at something, right? Now, in the opposite scenario, say you're looking down on something. Like, let's say, you're in a helicopter. And so let's say this is your helicopter that you're in. Okay, you're looking down. You're flying in the helicopter. You're looking down at someone on the ground. Okay, so this is the person sitting on the ground or standing on the ground, wherever. All right. So let's take a look at this scenario. So in this case, if you're standing in the helicopter, say you're here, this is your eye level, so this is your eye here, right? This eye level here, this is your horizontal axis. Okay, so this is your horizontal axis here, right? And you're looking down on someone, so now this is going to be your new line of sight. So now the line of sight is, whoops, this is why you guys should use rulers. Right? Line of sight is the distance from where you are to where the person is. Okay? And if you look at the angle that's created between the horizontal axis and the line of sight, and let's do this in green here, this is your angle of depression. So I'm going to use theta sub d to represent angle of depression. In both cases, it creates a 90-degree angle. So because it creates a 90-degree angle, whether you're looking at angle of elevation, if you're looking up at something, or angle of depression, if you're looking down at something, you can always use your primary trig ratios. You can use your SOHCAHTOAs. Okay, so keep this in mind. We'll do some questions regarding angle of elevation to angle and angle of depression. These are just some concepts that you can understand. Right, so try to understand the horizontal axis, the line of sight, and also this height that's being created, right? So the height is basically the vertical distance from what you're looking at to where you're located. Okay, so that's the idea. We'll do some questions to kind of enforce these concepts. All right, let's take a look at another application of trig ratios. Here we have a problem-solving question. A squirrel stands 2 meters away from a tree. It is looking at a pine cone and the angle of elevation is 40 degrees. How high does the squirrel have to climb to reach the pine cone? Okay, so let's draw a diagram. The best way to do these type of questions is to do diagrams here, right? So let's say that the squirrel is located here, right? And there's a tree that's, it's located up here. Okay, so there's this tree here that the squirrel is looking at, Okay, and then it's looking at like a pine cone here. So let's say it's looking at this point, right? Okay, and you can just kind of draw some leaves here. But let's say that the squirrel is looking at this pine cone, this object here. Okay, so here's your squirrel, and it's 2 meters from a tree. Okay, so let's say that this distance here, this is your squirrel, it's 2 meters from the tree, right? And it basically looks up at the pine cone. So the squirrel is looking up at the pine cone. We're going to assume that the squirrel's height is negligible. And when I say height, I mean the height of the ground to its eyes, because squirrels are basically on their 4 feet, so they're not too far elevated above the ground. Versus a person, for instance, right? They're going to be standing upright, so then you can factor in their respective height to their eye level. So in this case, you can see that this is the horizontal axis, or this is basically the original eye level of the squirrel, right? And then this here is the line of sight. This is the physical distance between the squirrel. It's a diagonal distance between the squirrel and the pine cone. So the pine cone's here, right? And what we're trying to do here is it's trying to climb up the tree. Well, how high up the tree is this pine cone is what it's asking. Because it's a height, it should be a 90-degree angle. Okay, so we know this is 2 meters. We know that the angle of elevation is given as 40 degrees because the angle of elevation is the angle or the degree of rotation from the horizontal axis to the line of sight. You can see that it's above the horizontal axis. If you want to find their height, if we look at using our SOHCAHTOA analysis, this is your opposite side to this angle 40 degrees. This is your adjacent side because your hypotenuse is always opposite the 90 degrees. So this is your hypotenuse. And you can see that you're given the adjacent side, you're not given the opposite side. So we want to solve for the opposite side. I would tend to use my tan ratio. So I'm going to do tan 40 degrees is equal to height, which is the opposite side, over the adjacent side, 2, right? And you can get this from your SOHCAHTOA mnemonic, right? Tangent is the opposite side over the adjacent side. In this case, tan 40 is equal to h over 2. To solve for h, I'm going to multiply this by 2. This cancels out. Whatever I do to one side of the equation, I'm going to do and repeat to the other side. So h is equal to 2 times tan 40 degrees. So h is equal to, and I'm just going to punch this in my calculator to see what I get. 2 times tan 40, and that's going to give me 1.678. So let's round this to 1.68 meters. Okay, so how high does the squirrel have to climb to reach the pine cone? It's approximately 1.68 meters that it has to climb up.